Hello, Eugene Aiello here again for our second video in the series. I just wanted to do a little recap on that last video. Went very long, I'm sorry about that. It was very fun to upload onto YouTube, but important point I was trying to make in that video that I might have kind of slid by and not reinforced enough was electromagnetic energy is very vital when it's absorbed into pigments. In the last video, we discussed cytochromes in the mitochondria, but cytochromes are all over the body, by the way. Skin pigments, melanin, cytochromes, amino acid rings all have the ability to absorb electromagnetic energy, which will excite electrons to higher levels, making them more likely to donate electrons. What that's actually doing is creating a charge separation. So electromagnetic energy is absorbing into biologic tissues and creating a charge separation, which is a potential to do work. All life processes are driven by these charge separations that occur. Those charge separations, we're going to discuss how this goes throughout the body, but that electromagnetic energy transfer throughout cells and within cells is driving every different reaction, which is going to be broken down piece by piece as the video goes. We spent a lot of time on the mitochondria though, just because when I began my research, I ran into that issue and I learned about the Merburn model. When you take into account electromagnetic energy can be driving every process in life, you're going to have to look at biology and all the models, the very complicated models, by the way, that I learned in school. And if any students or professionals are out there, we had to learn all those steps. And we just kind of learned the pathway. We learned there was an enzyme that catalyzed the reaction, but we never took into account how these things are actually happening. What's the behind the scenes? What's at the quantum level? How are enzymes creating a reaction that results in a new product? It seems like biology likes to use shapes and fitting and just charge of this and charge of that, but it's much more complicated, much more simpler than that actually. And that electromagnetic energy is just creating charge separations which allow electrons to move to different particles. Redox chemistry basically, which is reduction, adding of an electron, or oxidation, taking away an electron. So it was very important that my first steps in my research told me conventional models, they're up for grabs at this point. Any one of them can be remodeled, just like the Merburn model remodeled the mitochondrial system. So Merburn applies to mitochondria, obviously, but Dr. Morali, he has spoken at great lengths at how it applies to multiple processes. Anywhere that there's a cytochrome in the body, you're going to see a Merburn reaction. So there's cytochromes within the liver, there's cytochromes within the pituitary gland. Steroid production is also going to be driven by electromagnetic absorption, inducing the oxidation reduction reactions that create active hormones. So Merburn basically created a whole new idea in enzymology. We have two types of enzymes. We all learned in school about classic enzymes. Classic enzymes have a deterministic specific reaction, meaning A plus B is going to come to C. So one substrate, another substrate are going to bind to an enzyme, shape and fitting again. So those are affinity binding sites is the way I'm going to describe them, not lock and key shape fitting. But when those two products are joined together, this enzyme is going to catalyze that reaction. It's going to make it happen immediately. What's actually occurring in these reactions to make A and B turn to C? You guessed it, oxidation reduction. We're moving electrons to change how the compounds interact. In theory, if A and B were all by themselves and there was no enzyme, A and B over time could probably go into C. But the idea of an enzyme is it's going to make that reaction happen faster. Now we move to a merzyme. Merzymes are non-probabilistic, meaning they're versatile. They can have all kinds of different outcomes depending on what substrate is added to it. As a perfect example, we're talking about the liver in this section for enzymes. Livers are metabolizing xenobiotics, foreign particles, which can be dangerous to the organism. Well, if you ever pick up a package from a processed food, it's pretty much regular that you're seeing new things inside that food. How does our liver know how to metabolize these different toxins? These different configurations are genetically encoded, meaning there's a genetic code that produces that enzyme. How rapidly is our genetics going to alter to be ready for that new toxin that's added to our food? This is where this comes in. And I think it's a major part of how our body is detoxifying. So In the liver, you've got cytochromes again. You'll have affinity binding sites. These binding sites aren't going to be as specific as back in the mitochondria where it's binding ADP, so it's near that Ross reaction. These binding sites are just going to have certain affinities to different molecules. The complexity of that can get big, meaning there could also be multiple types of binding sites. But any one of these toxins that now enter the system, and we're going to call that toxin question mark, when it interacts with Ross and any charged particles, phosphates, sodium, whatever is in the liver, however this reaction is going to occur, that Ross-driven reaction is going to reduce that new thing, allowing it to be bound to. That's phase 1 neutralization and redox metabolism in the liver. So the liver can function in a very versatile way with a Merzyme model. This also gets into another concept, which we're going to delve into deeper. I think the entire body works by many deterministic mechanisms. So things that the body does regularly, it's going to have a binary type situation, meaning it's going to happen or not happen. Nervous system, as we're going to discuss later, nerves fire or they don't fire. Well, that's a deterministic, very limiting model. When you take in the Merzyme concept, now you're moving into quantum mechanics. It's versatile. So if there's a quantum system within the body, which there is, which is the model I'm proposing, you have multiple outcomes that can happen. So moving into that concept of binary versus quantum, binary is 0 and 1. So when I gave the example about a nerve, it's either going to fire or not fire. When I've got a classical enzyme, same concept, you're going to have a specific reaction. It's going to be this, and then that. Quantum gets into a whole different realm. Quantum works at wave energies, electromagnetic wave energies, and that's why I'm bringing this up. So electromagnetic interactions within the system have a quantum effect. So you can have multiple outcomes. You can have that binary 0 and 1, but you can have anything in between as a probability. As you get into more complex things, which quantum physics gets extremely complicated, you can even have it being 0 and 1 simultaneously. I won't explain that. If you look into the Young's experiments with the splits and photons going through those slits, that those photons could exist at both slits simultaneously. You can read about that, Young's double slit experiment. But my point being here is electromagnetic energy interacting with those proteins, those cytochromes, those melanin pigments. Those different energies are going to have different reactions within the system as the system has that energy flow through it. Simplicity that I keep mentioning is the charge separation, but as we get further into this series, you're going to find out that there's more to it than just the simplicity of plus and minus charge separation. That's how quantum mechanics is interacting in the binary realm. So it's doing material changes within molecules and structures, but that's not all electromagnetic energy is doing. It has quantum interactions with protein networks. So pretty simplistic. I want you to get this out of it, that electromagnetic energy is creating a charge separation that's vital for every process of life. But I also wanted to touch on the fact that this quantum energy, this electromagnetic energy, is interacting with the system. And there's more to it than just causing classical reactions within the body, such as in enzymes and Merzymes. There's a communication network, and it's not carrying data within the communication network. The data is within the protein structures that electromagnetic energy is interacting with. So we're going to have that as a whole topic in another video, but I want you to take away that electromagnetic interactions with pigments, cytochromes, proteins, rings are creating absorption of that energy, and they're creating a charge separation that's utilized for work within the cells and within the body.